What's today? 9? Yes, no?
9,
Maybe?
9, 9.
All right. We will. We will go ahead and get started. First off, we have 2 organizations, student organizations, that are going to talk to you. I am the faculty advisor for both. The first one is the American Society of Mechanical Engineers, or ASME, and the second one is the Society of Women Engineers, or SWE. And we have representatives for both here who are going to take just a couple minutes and talk about upcoming events and how you might want to participate in the organizations. It's good to start now. And then we will have our speaker today, Dr. Brian Williams, and he's going to talk about his experiences as an engineer in the workplace. He worked for several years in industry before he came to ISU. You will need to write a short summary, no more than a page, okay? No more than 1 page, single-spaced, with regard to Dr. Williams' presentation, all right? And does everybody know how to upload on Moodle? If you've gone to Moodle recently, you'll see a little heading there that says Brian Williams presentation or Brian Williams summary. I can't remember which I put there. You will click on that and be able to upload your document to me. I would like the documents either .doc, not docx, or .pdf. Those are the only 2 formats I want, okay, or will accept. All right? Okay, well, we'll go ahead and get started. We have Brian Kanan. Abhishek, are you going to come up too? No? Okay. Well, you can stay back there. Brian can introduce you. Brian is the president of ASME, and he's going to take a few minutes. Here you go. You need this.
Did anybody here, have you guys heard of ASME at all? Anyone? It's kind of relatively new. Well, online?
Speak up, so we can hear you back here.
Well, like Mary said, it's a student-led organization, and it stands, American Society of Mechanical Engineers. And what we kind of do is like a fellowship of mechanical engineers, and our big thing that we're doing this year is design competition. So we're part of a design and build team where we're working on an RC car, and then we're going to travel in the spring to go compete with our design. And so what we're trying to do now is really recruit some students for just help in joining our team and just working with us on our different projects and fundraising events and things like that. And I'm just going to pass this paper around. If you guys at all are interested, can you go ahead and just write your email down there, and I'll get back in touch with you. What we have here, just some advantages. The membership is free if you're a freshman, which is kind of a good deal, I guess. $25 if you're not a non-freshman. And I think that includes also like a free subscription to the ASME magazine as well. A big thing that we kind of gained from our class or our club is just getting to know other students who've possibly taken other classes before you or have more experience in other areas, and so you kind of get to know each other, and they can help each other with homework, and you can borrow textbooks if someone's taken that class before you, and it's just a good way to meet other students who are trying to achieve the same educational goals as you. And then, like I mentioned before, our project design competition, that's really where we have the most fun, is when we're working through with different SolidWorks software and trying to design different projects and things like that. And so it's really a lot of fun when you kind of get into it. a lot of times what happens is we kind of wait till the last minute to get everything done, and so I don't know if you guys are like that at all, your homework or anything. But this year we're really going to try and hit it hard early and work on trying to get some SolidWorks models built for this RC car. And so we really need people who are good with computer software, who want to do analysis and like to see things move fast and mechanically inclined and have good ideas. So that's kind of where we're at. This is my email address right here, kanebria@isu.edu. I really encourage anyone to just give me a call if you have any questions, or not call, but email. I put my number up there, but just give me an email. And if you have any questions at all, if you're somewhat interested a little bit, I mean, I'm busy sometimes, but I'll definitely do my best to get back in touch with you and just kind of fill you in. And if you just have any questions about ISU in general, I don't know if you're all freshmen here mostly, but kind of wondering what mechanical engineering is all about, if you're interested at all, and you know, if you decided what discipline you want to go into yet or not. But definitely there to answer any kind of questions. If you just, I don't know, I've been here, let's see, 6 years now, so kind of got a good idea of what's going on. Yeah. All right, that's about it.
Why 6 years?
I actually started off in pre-architecture, so I kind of changed majors around and took some other classes. But thanks for asking.
Brian likes it here. We have a mic that's on, and so we're getting some feedback. Would you please check to make sure that your lights aren't on? Okay? Thanks. All right, we have Amanda Finks now, who is the president of the Society of Women Engineers.
So I don't know if he said this, but first of all, I'm going to encourage all of you guys to join your professional society. Yes.
Could we have the Elmo, please?
So I'm going to encourage all of you guys to join your professional society, no matter what it is, because it is a really good way to get to know others in your discipline and be able to network with them, so that we all have an idea of what we went through and we can help you guys along the way. We know about the books. We know about everything that has to... We know about the professors, okay? But you have a network of people then that have gone through what you're going to go through and can help you along the way. So even if you don't do anything else, I really encourage you guys all to join your professional societies. Now, back to focus to SWE. So SWE is a different society. We're the Society of Women Engineers. It's not a sexist group. Men can join too. In fact, we used to have a male president. But SWE is more of a networking society than a professional society. What we do is we put on different competitions for middle school, high school girls. We put on the engineering picnic. We're more of the networking. We're more of get to know who else is in your class and get to know other people in other disciplines, whereas the professional society, you only meet and see other mechanicals or other nuclears or other civils. So it's more of an interdisciplinary group, and basically our point is to go and have fun. Our first meeting is this Thursday at 5:30. I'm also going to pass around a list to get emails if you guys are interested in joining, and that way you can be added to the email list. And I think you guys should all come out to SWE. The other thing is, I know last week Mary sent out an email about the ANS barbecue, the American Nuclear Society. We're having another one also this Thursday, and that one's at Ross Park. So if you didn't get a chance to go, you guys can still join that group too. Do you guys have any questions? Perfect. And my email's up here. If you guys do have any questions, feel free to contact me. Thank you, Mary.
You're welcome. Those of you who are in Idaho Falls, if you are interested in SWE or ASME, please note the emails that were listed here. The little PowerPoint that Brian showed is posted on Moodle, so if you missed his email address, you can find that on Moodle. Okay? All right. Well, what we're going to do now is Dr. Williams is going to come up and talk about his experiences as a engineer, mechanical engineer. He's one of the faculty in mechanical engineering and teaches upper division thermal fluid type things, and so you'll see him later on in your career here. There you go, Brian.
Okay, what I think I might do is I don't have a PowerPoint presentation, but some of the projects I worked on, I noticed there are pictures on the web, so I might just pull up some pictures off the web to show you when I start talking about projects. Before I came to ISU, I worked for 3 different companies. The first company I worked for was Lockheed Martin Missiles and Space out of Sunnyvale, California. I worked at Palo Alto at what's called the Advanced Technology Center, which used to be the research labs, right across the street from Hewlett-Packard's headquarters, stuff like that. She wanted me to say, what's in the typical life of an engineer? What does a typical engineer do? And I was kind of joking with her. You show up to work, get a cup of coffee, check your email, talk to the guy next door about last night's game, noon, check your stocks to see how your stocks are doing, stuff like that. So there's a lot of stuff like that still happens. But some of the projects, the group I worked in, I was a mechanical engineer in the group, and we were the mechanical and thermal systems group. And in short, we made popsicles that you put in space. So, and I don't know if there's any pictures of this stuff to find because they tend not to put classified projects. I never worked on any classified projects where I needed a security clearance, but everybody's heard of spy satellites. Lockheed made spy satellites for 40 years. That was kind of their bread and butter. And these satellites they're big. They're like the size of a school bus. And the funny thing is when they built the Hubble Space Telescope, it was built in Lockheed, and right next to Lockheed is an Air Force base, Moffett Field, has a bunch of big hangars. If you've ever been down in the Bay Area, there's a bunch of really huge buildings where they used to put the old blimps in and stuff like that the Navy used to play with. That airfield, they can land the big C5 Galaxies on. And the big C5 Galaxies, the nose opens up, and it allows them to put very large packages in. And when they loaded up the Hubble, they had a shipping package that was exactly the same size, just happened to fit the Hubble, just kind of coincidentally. And they loaded it right up into C5 to ship off for NASA to launch. So they've been launching these spy satellites for a long time. In the old days, back before they came up with digital photography and digital videos, they used to have a film canister. And the way they would work it is these satellites would be up there orbiting around taking pictures of Russia or something like that, Cuba. Then they would kick a film canister out and it would come down in a parachute. Then they had a big airplane that would fly by with a hook and grab the parachute and get the film canister and take it in and develop it. That's how they used to get the pictures. Now, anybody ever seen, what's that show, Patriot Games? I think it's one of the Tom Clancy books, where they talk about the spy satellites and that. And they kind of talk a little bit about the resolution, and they can actually get real-time images out of those systems now. There was a show on one of the documentaries on one of the science channels where it talked about some of the spy satellites, some of the unclassified information, and they were trying to see the quality of a spy satellite. And what they could do is they put some grapefruits on a picnic table and had as the satellite. If you talk about something in orbit, you can't just, it's not like your car where you can just change directions. It kind of wants to follow its same orbital path. It takes a lot of energy to change orbits. So they had this satellite flying overhead, and it would take pictures, and they would ask the people how many grapefruits you see. And they put 3 grapefruits on the table. It flies over. They ask the people, how many grapefruits do you see? 3. Okay. Flies over again. How many grapefruits do you see? 3. So they move the middle grapefruit. It flies over again. And this is from, 200, 300 miles up in orbit. It's taking images down at the Earth, and it noticed when they'd removed the grapefruit. And that's what they're telling you it can do. So imagine what it can really do that they're not telling you. They're talking about reading, like the Hubble Space Telescope can read a dime if you were to take a dime and put it on the limb of the Earth, the Hubble telescope could read that dime. So think about if you take one of those things and point it at the Earth and you wanted to take pictures. So they take pretty good pictures. They built the entire spacecraft there, the whole satellite. And the group I was in, I said we built popsicles in space. We built the cooling system. A lot of these satellite imaging systems have visible cameras. Everybody, you guys familiar with like the electromagnetic spectrum? There's visible light, which is what we see, 0.4 to 0.6 micrometers. And then there is infrared, which is going to be the stuff, the heat, the stuff that sees heat and things like that. In order to have a camera that can see heat signatures, it has to be cooled. And so the question was, how do you put something up in space where, one, it costs a lot of money to put it into space. I want to say the space shuttle, something like $100,000 per pound to put some type of payload in space. So it costs a lot of money, and how do you fix it if it breaks? I mean, everybody's seen the pictures of the space shuttle that comes up and grabs the satellite and pulls it in, and they fix it and send it off on its way. That cost about $1 billion for one of those missions. These satellites cost like $100 million, so it doesn't make a lot of sense to spend $1 billion to fix something that's worth a tenth of its value. So you want it to last a long time. Things like reliability become very key. So you got to make a system that'll stay cold and it's reliable. And when I'm saying staying cold, I'm talking about freezing hydrogen cold. So about 13 kelvins in temperature. So 13 Kelvin above absolute zero. And I say it's a big popsicle because what happens if you put liquid in space with no gravity? Float around, right? Okay. So say you have like if you wanted to use liquid nitrogen to cool your system. Okay. So you have a bunch of liquid. I'll try the Elmo. Let's draw a picture here. You have a big tank, and there's a rod coming out here, and this thing here. That's your detector, okay? And this is your tank. If you put a liquid in here, that liquid's going to float all over the place. It's just going to kind of bounce around. Every time it fires a little rocket motor to change its direction, that liquid's going to kind of slosh to the other side. And as it sloshes, it's going to cause the satellite to vibrate and bounce. If you're trying to take pictures and you don't want the satellite bouncing around, so what they would do is we would take a foam a metal foam and freeze hydrogen or nitrogen or something on it, CO2 or neon, a whole bunch of different systems. So you would freeze a bunch of a gas. The reason you'd freeze a gas is because you want something cold. Okay, you freeze water, 32 degrees Fahrenheit isn't really that cold. So we're talking like really, 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 really cold cryogenic temperatures. And so you'd freeze a gas on there. And as I'm saying, it looked like a big popsicle. You got a stick coming out, which connected the detector to your heat sink. And this whole big thing here would be some frozen gas. And that's how they would cool the detector. Then up above here, you'd have your telescope. Oops, that's a bad picture. Anyway, there'd be a telescope up here above it. And that's how so if they wanted to take pictures of something and they wanted to do the infrared region, they'd have to take this cold big device, point it at what they're trying to point at, and take a picture. And I'll talk later about another projects I worked on. How do you make things turn in space when there's nothing to push against? You ever been in a swimming pool and tried to turn? Try doing it with nothing, with no vacuum or anything. How do you turn stuff like that? How do you make something spin? Kind of the funny thing about this, these are extremely classified projects. There are people that had security clearances, and their security badge was kind of funny. It would be a checkerboard. And in that checkerboard, there'd be something like this. You know, maybe a smiley face in one. Who knows what they did. But what happens is, if somebody had the same mark in the same box, you could talk about your project to them. It's called compartmental security. So people only know their own part. So these guys they would work on this. They would build these systems, and it was extremely, extremely classified stuff. When they say top secret, hear about top secret in the military, this is beyond top secret. And so we're sitting there one day, and we have all these pictures of our big popsicles. We make a big popsicle, we give it a name, Clay's. They put a picture of it on the wall, so as people would come into our building, there'd be pictures of all of our projects, kind of showing off your work. So one day, we're sitting there looking on the internet, and we found pictures of one of the old satellites. It's called the Keyhole, KH-11, Keyhole satellite. I can't remember the website, or I'd bring it up. It's probably long gone by now. But we're sitting there looking at it. We're kind of talking about it, and I'm looking at the front end of that, and I walk out in the hall and look at the picture, and I walk back in and look at the satellite picture again. I go, hey, that car cooler system's in this satellite. And they're like, shh, don't say that, We can't, I could see it, but they couldn't tell me that was what was up, because they would get in trouble for telling me. So I worked on projects that were classified in nature but never had a security clearance, which is kind of nice, because if you have a security clearance, which is if you go work for the DOE up at the INL, or you go work for one of these aerospace companies or something like that, and you have to get a security clearance, if you ever travel, you're a U.S. citizen, you ever travel and talk to somebody from certain countries, we'll pick on Russia. How's that? Nobody Russian in here? Russia used to be the bad guys. We'll say you talk to somebody from Russia, you have to go back and tell everybody who you talk to, or they'll arrest you for spying, stuff like that. So to me, they're kind of a pain in the butt, so I didn't care to have one. We worked on another project where a guy came in. We had a test we were doing. We were testing one of our popsicles. We were cooling it down, and we were going to do some testing on it, just some thermal testing, add a heater, see what happens. And we were going to test for 3 days, and I had some guy come in. My boss walks into me and says, Brian, this is so-and-so. And I don't know the guy's name. I swear the guy's name was Ben Dover, and I'm not kidding about that. They used to use fake names. Ben came in. They go, this guy's Ben. And my boss knew who he was and was being really, really, paying a lot of attention to him, making sure he was happy. He's going to watch your test for 3 days. So I'm like, well, who is he? They're like, don't ask. You don't need to know. I think he was with, what is it, NSA? Is that the one I think that, well, no, anyway. That was my guess. But, so the guy sat there for 3 days. We talked, everything. I never knew his name. I never knew who he worked for. He was our customer, and we tested our device, and he left happy, and that was it. Probably went into a satellite somewhere that we have I don't know anything about. But anyway, so there was a lot of stuff like that. We made thermal systems. My work involved a lot of thermal analysis, a bunch of thermodynamic analysis. If we go back to our popsicle here, what happens to a solid, say nitrogen, when it sublimates? Everybody know what sublimating is. If I say melt, you know what melt is. Melt goes from solid to liquid. Sublimate goes from solid to vapor. The whole key here is you don't want to have a liquid. You want solids, you want a vapor. What happens if you take an enclosed tank and you add heat to it and you change some of that solid into a gas? It's going to happen to your tank pretty soon. It's going to blow up, right? Guys, dry ice bombs, everybody knows about dry ice bombs? Dry ice bomb. But this isn't CO2, this is like hydrogen. Imagine the amount of energy in 1,000 liters of solid hydrogen. I mean, it's like enormous amount of energy. So picture this as a dry ice bomb. If you don't release the pressure, it's going to blow up on you. And so as you're adding heat into your popsicle and you're losing some of your solid stuff and it's turning into some gas, you have to vent it out. So there was a bunch of analysis. How do you insulate it? How do you support it? How do you hold, if you have a cold popsicle that's like really, really cold, say 13 Kelvin, and you have an outside of a spacecraft, so this is 13 Kelvin, This is 300 Kelvin. How do you hold this without letting this hot surface kind of heat up your cold surface? So there's a lot of tricks we had to run with supports to try and hold this in place. The other thing is not only do you have to hold it, you ever seen a rocket launch? It's not exactly a smooth ride. It's kind of a lot of acceleration and a lot of shaking going on. So anyway, that was what, so we would do, there was people in my group that would do the mechanical analysis. If it cost $100,000 a pound to send something into space on the shuttle, it's probably a good idea to make it as light as possible. So you're not going to take this tank, this high pressure tank, and you're not going to go down to your local gas store and get a big huge K bottle that's like 2 inches thick or something, because it's going to be heavy. So we had guys doing structural analysis to make the tanks as light as possible, thermal analysis. It's amazing the number of electrical engineers and computer scientists that are involved in the aerospace industry. Probably half the teams, or half the people on the teams I was on were electrical engineers, because you don't put people up there with it to ride along to operate it. Everything has to be autonomous. You have to take data, you have to communicate. Everything you can imagine has to be done autonomously. That usually involves electrical signals and computers and stuff like that, and lots and lots and lots of code to tell it what to do. Some other stuff that I was on, let me see if I can get a picture up here as I keep talking. I'll get this thing to work. How many of you remember, I guess it's called the First Persian Gulf War, 1990? Who's ever heard of a Scud missile? Does that bring, some people you might have heard? A lot of you guys are probably too young to even know anything about this. So it happened when you were either born or not quite born. But a Scud missile was a type of missile that really didn't do a lot of damage, but it was kind of scary because they would launch it, nobody knew where it would go. And the U.S. had something called the Patriot missile. Everybody's heard of the Patriot missile? And the idea is they shoot a missile in at you, you shoot another missile at it and hit it. Except the Scud missile would break up, the radar would track 10 pieces, and they'd shoot 10 missiles at 10 pieces, and there was missiles going all over the place. Wasn't super reliable. So anyway, they started coming up with a bunch of different projects. One of them was called the airborne laser. Where's a nice picture? I just looked this up a second ago. Here, see how this looks. Does that look very good? Can you see that? Kind of? Maybe? I can't zoom it in or something, but anyway, you've got an airplane flying here, and as somebody shoots a missile, the idea is that you use a laser to hit the missile. Okay. One thing you learn about, if you ever take any aerospace classes, are that rockets are long and thin and pointy at the top and have fins at the bottom. And there's a reason they look like that. There's a reason rockets are long and thin. And it has to do with aerodynamic pressures. Rockets travel very fast. If they were fat, they would have a lot of pressure on them, and there'd be a lot of drag, there'd be a lot of forces on them. So the idea is to make a rocket long and pointy and thin. Fins at the bottom because it has to do with aerodynamics and stuff like that. So the way the airborne laser would work, let's find another picture here, maybe of the airplane. See if this one works here. There's a picture of it. It's essentially a 747 with a controlled rocket engine that fires a laser. So back in here, in this part, there was a coil laser, chemical oxygen iodine laser, coil laser. And there was a bunch of electronics. They would
B-16.
What?
We need an operator in B-16. We're not seeing what you're getting.
What happened? Oh.
Go ahead.
Okay. Anyway. anyway, so you have something back here that's think of it, like I said, it's like a rocket motor, and it would chemically create a laser, and this laser would travel through here, and it had this big ball turret on the end. And this ball turret, as it would fly around, this ball turret could move to point and shoot. Lasers are fast, a lot faster than missiles. They found out with the Patriot missile, a Patriot missile was going fast, but a missile coming in is going a lot faster. So the idea is, let's use something even faster to shoot down the missile. And this isn't like Star Wars, where the missile would hit and you see this big explosion or something like this. The way the missile would destroy, or the way the laser would destroy the missile, is it would heat the surface up. Remember I told you rockets are long and thin? Okay. And you've got a very large force on this rocket. You've got your thrust and you have your drag force. The idea of the laser was it would shine into here, and essentially this rocket is a thin skin object. And so the laser would heat the rocket up until it would crumple under its own weight. You ever seen like an aluminum can? And you ever stand on an aluminum can and it'll support your weight, then if you tap the sides it collapses on you? Okay, same kind of idea. As long as the rocket's nice and uniform, it'll support the drag force. As soon as you do something to it, like heat the skin up until it starts to melt, it collapses. So the rockets would disintegrate. There wasn't this explosion or anything like that. It was just you melted the rocket skin till it broke itself in half. And there's a lot of issues with how you do that. There was an awful lot of electrical engineers and computer scientists involved in this. You would think it's an airplane, it's aerospace mechanical engineers. Well, yeah, there was. You had the it was a Boeing 747 that they just gutted it and filled it with everything they could to do this. Electronics, everything. This laser was on the order of terawatts. It was just a huge laser. And how do you know if your lasers, if your kill laser is what they call it, you want to make sure it's pointing at the missile. The idea is to hit the missile. You're flying over, say, a Baltic state, you're flying over Kosovo, somebody shoots a missile, you miss, somebody's herding sheep, charge sheep, something like that, right? I mean, it's incredibly, incredibly powerful laser. So it's very, very important it hits what it's aiming at. And so there was an awful lot of control mechanisms. Wow, that's funky. Okay. Something popped up on the screen here that was really weird. But there are an awful lot of control mechanisms. And everybody's flown in an airplane, and an airplane is not necessarily a smooth ride. So you've got a bouncing airplane, and on hot days you look through the atmosphere and you see a lot of distortion. There's a thing called adaptive optics, where the astronomers do this, where they'll send a laser out and they'll create a little image in the atmosphere, like a little star, a fake star. Then they look at the image with their telescopes, and if that is distorted, they change their optics so that it's not distorted. So they can cancel out all the distortions in the atmosphere. That's probably a good thing to do when you're shooting terawatt lasers from up high down towards the ground. I mean, you want to be able to get rid of the distortion in the atmosphere. And so our job, the part I worked on it, this is not a project to where you have like 3 people like your senior design teams. This is not a 3-person, you're going to go do this in a year type of project. This is like a multi-year, 3 main companies involved. Boeing was the lead. It was their airplane. Lockheed did all the control, and TRW made the laser. So there was 3 companies that worked on this. We worked on it for, I know they've flown it now, but it's probably been 5 or 10 years. And our team alone Lockheed must have had a few hundred people involved on it, a few hundred engineers. My particular group was involved in what went into this turret here. It goes back to you need a reference point. Okay, and everybody's heard about gyroscopes. Gyroscopes are like tops that spin, and they don't change direction as you move around. They always want to be pointed in the same direction. So we had a system they were building, they were going to put inside the nose of this turret here, it was called the Inertial Reference Transfer Unit, IRTU. And I don't know if you want to write that down. Don't worry about that. That's too much to remember. But it was a device that had 3 fiber optic gyros on. And fiber optic gyros are extremely accurate, and they had 3 of them because they put them in different axes, so you could get 3-axis control of what was happening. But in order for a fiber optic gyro to work, it has to be held at an extremely constant temperature. So I was working with these, and control weenies, and that's what they called themselves, control weenies that were involved in controlling this. And my job was to make sure that we could maintain the temperature of these gyroscopes within like 1 degree of their set point. Oh, but you can't touch them. So you have to somehow control the temperature without touching them. And so it's amazing the amount of analysis and testing that you can do to prove that. Because when you get out and start working, everything you do, you do a lot of analysis in your classes. You'll take statics, 210, you'll take dynamics, you'll take a bunch of classes, and it's all solving problems and doing analysis. Then you start getting to do some fun stuff, and you start getting to do design. And design's really fun, except saying you can design something and saying you can make it work are 2 totally different things. If you say, I designed this, nobody's going to trust you. You have to do testing, and that's usually what you see. You see in the design process, you see high-end tools being used, computational fluid dynamics, computational mechanics packages, finite element analysis. Brian Cannon talked about solid modeling, using like SolidWorks. You do a solid model, then some people will analyze it for structural, some people analyze it for thermal. So you're going through doing all this, but you have to test what you build or you have problems. An example is a company called Orbital Science. They designed this thing called the Pegasus rocket. They drop it off the bottom of an airplane, and they fly at 40,000 feet, drop this rocket, and then it launches up into space. And they made some change. They had built their system. They felt really comfortable with it. They made a few changes, and they did some modeling, no testing, and said it's going to work. And they put a $100 million satellite on it. It went to launch. I saw the video footage. You see it go up, and you see it start rocking. You're looking behind in the camera, and you see the Earth, and you kind of see the Earth passing by as you see the space, and you see the Earth in space. It starts tumbling. And they had to detonate it and lost their $100 million package. And because they didn't test to prove that it worked. So remember that. Whenever you do any design, it doesn't matter until you do testing. So there's a lot of design, there's a lot of analysis, but then there's also testing. Can you make it work? And usually there's a term out there called as-built drawings. That's usually because how something's designed and how it actually works are 2 different things. So you design something and you have a drawing package. Then by the time they build it, you might have a different drawing package. And by the time they make it work, it's changed again. So things like that change as you go along. Anyway, I mentioned about satellites. Kind of look like a satellite. Okay. Maybe the satellite is spinning. Just like when you throw a football or something, it spins. A bullet spins for stability. Satellites spin for stability. How do you make a satellite spin, or how do you make something spin when there's nothing to push on? You know, if you throw a football, your hand, as you throw it, causes the football to spin. Once it's in the air flying, what's causing it to stop spinning? Somebody. What?
So isn't that solar wind that they use to make those spin?
Solar wind is a torque that is applied to satellites that can kind of restrict your motion. or they make solar sails that can actually use to propel you, but they're very, very, very low force because the force of a photon striking a surface is very small. They're traveling fast, but they don't have much mass. So, but the way you do it is, go ahead. You got to talk in the microphones, though.
My microphone doesn't work.
Okay.
What I've been, because since there's nothing in space to
It's a vacuum.
yeah, to interact with it, if you impart spin when you release the satellite,
It'll
it
spin.
should technically continue
It'll
to
keep
spin forever.
spinning, and it won't stop unless the energy damps out. And if you ever want to see energy damping, take your soda bottle, throw it with the half full, spin it and throw it in the air. Spin it about its long axis like you would a bullet or something like this. You'll notice it'll stop, it'll start wobbling and start tumbling. The energy dissipation of the liquid inside the bottle causes your bottle to lose energy. As it loses energy, it changes its axis it rotates about. When it will rotate, it'll turn into a tumble. Kind of physics, physics always works against you, it seems like. Friction's bad. Things, when they lose energy, they tend to tumble. Okay. So yes, something will continue spinning when you release it, but what if you want to change it once it's released? And one way to do that is what if, how can I draw this? What if we put some rocket nozzles, and if I want it to spin this way, I would push, I'd fire this rocket nozzle and fire that rocket nozzle. So you make what's called a couple. So you have a torque, force times the distance. You have two of them, which makes a couple. And if they're the same distance and they have the same force from the center of rotation, then you can change the rotation of it. So they use little rocket motors, okay? If you have a rocket motor like the space shuttle, you don't shut off the big engines on the space shuttle. Once they fire them, they're going. You don't turn them off. They burn till they're done. The only way to stop the space shuttle motors is to split the casings and let them kind of explode, which isn't good for what the people on board. So it's not a good thing to happen. So we worked with this product called hydrazine. Hydrazine looks like water, has the properties almost of water, but hydrazine, if you run it through a catalyst, and if you remember back to chemistry, a catalyst is something that just accelerates your chemical reactions. So a catalyst causes the hydrazine to go from a liquid, say at room temperature, to a 1600 degree Fahrenheit gas. So we would have a hydrazine tank, and we'd run it through a catalyst, and it would go from a liquid to a high temperature gas, high temperature, high pressure. You would blow it out there just like just like your garden hose. You pick up your garden hose and it wants to push on you. Same idea. And we would use hydrazine. And something like in the company I worked for was called General Dynamics. It was up in Redmond, Washington, and it had originally been. I interviewed, got a job offer from a company called Primex. I went to work. Everybody's badges had stickers on that said General Dynamics, and a year later they were sold off to Aerojet. So people worked for the 3 different companies and never left their position. The companies were bought and sold. But this company, something like 99% of all satellites that are launched have hydrazine systems on, and this was the one company in the world that made hydrazine. So it's kind of like talking about cornering the market. So they did hydrazine, and that's the whole system we built. Hydrazine, the Mars Viking landers and all the Mars new landers they're doing had hydrazine engines on them. Every satellite has a hydrazine engine on it. So these guys were the pros at doing hydrazine. And so there was a lot of thermal analysis and structural analysis and fluid dynamics analysis going into what happens when you start with a liquid and you want to get a hot gas. And you want that hot gas to come out of a place, and the nozzle is going to get hot, so how do you keep that nozzle from melting? So there's a lot of things that go into how you design stuff like that. If you look at the space shuttle main engines, their nozzles, they actually flow the liquid hydrogen through their nozzles to cool them, and then they flow it into the combustion chamber. So there's things like that you can do. one more company I want to talk about. I didn't just work for places that made weapons. That was the mistake I made on the airborne laser. I was on the project. We're at a meeting, and we're talking about the airborne laser. And I'm like, and it's hard to shoot down missiles. And I said, well, isn't it easier to shoot down an airplane? And I kind of was chastised because they were selling it as a defensive weapon. They did not want to project to people that it could be used as an offensive weapon. And so I didn't just work for warmonger companies, if you want to call it that. However, when the nation economy goes down because of our war, my Lockheed stock went up. So it's kind of an inverse to the market. But I worked at another company called Cryofuels. And it was a good company. It was a good green renewable company. The object of cryofuels was to take landfill gas, our first system. In Canada, there's a law that says that a landfill cannot let the gas naturally seep out. They had an instance that happened, I don't know how many years ago. Like most laws, something bad happened. That's why there's a law. They had a landfill, somebody came in, turned the landfill into a nice green lawn or something like that. Here. We'll get rid of that. Turned it into a nice green lawn. If somebody built a school on top of where the landfill was 50 years later, all the nice methane gases accumulated in a room, and there was an explosion. Something ignited it, an explosion, and blew up the school. So in Canada, you have to collect the gases and dispose of them. So they naturally have a manifold system. So they have a bunch of piping all over their landfills where they collect the gases and they kind of burn it in a big torch. So I worked for a company that said, hey, that seems like a waste of energy. Methane gas is something you could use. Except methane gas coming out of a landfill isn't very pure. Natural gas, methane gas, same thing. It's methane, what is it, CH4. So what we did was we built a system that would take the landfill gas, plug into the pipe system they have, take the landfill gas, channel it through, clean it up, and then liquefy it. And then when you're all done, you have a big tank of liquid natural gas. And so if you had your dump trucks or your graders, whatever they have, you could use the gas from the landfill to power your vehicles. And all the power to run our plant came from burning the gas we were pulling off the landfill. So it was essentially taking waste stuff they would just burn, produce heat. We would use it to create natural gas that you could be used. Sometimes when they drill, they go into Wyoming or Texas and they drill a natural gas well. The gas that comes out is not pure methane. It's kind of a dirty gas. So you could go to one of those systems, tap onto it, clean it, and produce useful gas. And that's what that system does. You can imagine, since you had to liquefy something, there was a lot of thermal, there was a lot of controls, a lot of working with people like technicians, welders and pipe fitters and things like that. A lot of interaction with electricians and things like that. So I guess we're out of time. So anyway, any questions? Good, they're all asleep.
Okay. Thanks, Brian. That was... I always like listening to what he's done because he's done some fun things. And that's what engineering is about, doing fun things that you enjoy doing. And I think you could tell that Brian has enjoyed all the places that he's worked. Now, your summaries, I would like you to post them by Friday. Okay? So upload those by Friday. We have the next 3 weeks, computer science will be talking to you. If they're all uploaded by Friday, remember, I don't accept late homework, so if you don't get it in Friday, then you don't get it in. I will grade them over the weekend, and I will post the grades on Moodle for you, and have your papers that I don't know whether you want to pick them back up or not, but if you do, I'll make sure you can get them. Okay, but I will grade them over the weekend. So post them by Friday, and I'll grade them over the weekend, and you can see your grade probably on Monday. All right? Well, have a great weekend, and we'll see you on Monday.